Okay, next, chemical shift. We're going to talk tomorrow about how the NMR signals are actually measured, because there's a little bit of stuff then, if we kind of understand how they're measured, we can start to understand why they behave the way they do, okay? But we don't need to know that right now. Right now, all we need to know is that the frequency, in other words, where it shows up on the NMR scale, all right, is going to relate to the electron density. So in other words, if I have a hydrogen atom, it's got an electron cloud around it, and I'm going to draw that in just a little bit, okay? That electron cloud affects what frequency it is. And the relationship is actually pretty straightforward for signals that come below about 5, okay? So here's the relationship. Okay, so let me draw a graph here. So what this means is that what we're going to do is we're going to start here. This is our, basically it's our reference, I guess we'll call it our reference frequency. I got to go look at what the exact term for this is, because there's two different basic frequencies, okay? And then what we see is in this direction, the frequency increases. So up here we have a high frequency, and down here we have low frequency. And actually what we measure is the difference between the frequency for the signal and the reference frequency we take. So we basically measure how far is the signal shifted over from 0. And then we take a ratio, and then that's how we get our parts per million. And you don't have to do that math. I'm just trying to give you an idea of what the numbers mean. So high frequency on the left, low frequency on the right. So it turns out that if we look, high electron density causes lower, what that means is on the right, this is high electron density, and then this is low electron density, up to about 5. Well, after 5, we're going to see there's another thing going on with magnetic field. Electron density changes when we put in different electronegativity atoms. So let me show you an example here. So let's say we have a hydrogen atom. What I'm going to do is I'm going to represent the cloud of electrons with a circle like that, and I'm going to color it in. So this is kind of what I've talked to you about, how really in organic chemistry, I think it's often more useful to think of electrons as a cloud rather than a particle. And you can see that this cloud, the shading is really dark. That means there's a lot of electron density. If I put a chlorine right here, then what's going to happen is the chlorine pulls electrons because it's electronegative. So it takes electrons away from the carbon. Then the carbon takes electrons away from the hydrogen. And so what we get is the cloud is less intense. And so that's how we can visualize it. Just like, how intense is that cloud? It's like a gas or something like that, or like the fog, right? If the fog is really thick, you can't see through it. That's dense fog, right? If the fog is really thin, so it's sort of transparent, translucent, you can see through it. That's not very dense. Same kind of thing with electrons. Now, this kind of electron thing, this is called an inductive effect. It's just a term we're going to use again in second semester called inductive, okay? An inductive effect is electron withdrawing or donating, technically. It happens through the sigma bonds. You see how the arrow is really showing how the sigma bond is actually pulling the electrons, right? The single bond, okay? And it's caused, in this case, by electronegativity. But if I were to put an atom in and put a positive charge on that atom somehow, it would also pull electrons away. But here's the thing. So there's two things about inductive effects that you need to understand in order to see how the chemical shift works in the NMR. Once you get these two concepts, the NMR table and everything will make more sense. So the first one is that, and I'm going to draw a picture here. And what I'm going to do is I'm going to imagine we put a fluorine, an extremely electronegative atom right there. So then we look at our electron densities. Fluorine is pulling here, and then it pulls here. You see that this one here, this is a 2-bond effect, right? It goes through one bond and then a second bond. This is going to be the strongest. This atom will have a very low electron density. If we go one more bond away, this is a 3-bond effect. So what's going to happen is it's not going to be as strong. So this atom will have a little bit higher electron density. This is the 4-bond effect. And then this would be 5 bonds. And then this would be just a hydrogen by itself. This one is going to be the most dense. It's going to essentially be the same as the hydrogen by itself. And then this 4-1 is going to be in between. And I drew the 5th one so that I could get the 4-1 darker, but not as dark. So what we would then expect is that if we looked on our NMR graph, the 2-bond one would be right there. The 3-bond one would be here, just a little bit below 2. The 4-bond one would be here, just 1.3, 1.4. And then the 5-bond one and the one by itself would be here, let's say at 0.9. So this would be like 3.8. This would be like 1.9, 1.3, 0.9. Do you see as the density increases, it moves farther and farther to the right. And when we look at the correlation table, that's where those numbers come from, basically. So there's tables of these things. And I'm going to have to put the correlation table, but let me do one more thing, because this is one of the things that confuses people about the table. So this is our 2-bond inductive effect with 1 atom. But what happens if I put a second chlorine? Well, the first one is pulling, the second one is pulling. So now what I get is a pull and a second pull. So the electron density goes down even more. What does that mean? Well, that means that this one, if this one is at 3.8, this one is going to be up around 5.2. This is the problem with NMR correlation tables that we don't have quite so much in the IR one. When you look at the NMR correlation table, it's going to be telling you like the general, like if you have a thing pulling, it's approximately here. But a lot of tables, and in fact, my basic table doesn't have this. It doesn't account for what happens if I have 2 chlorines pulling, right? It doesn't account for the fact that these add up. And so you're not going to have an entry exactly where that peak is, or that peak is going to come here, but it's not really for this thing. It's for 2 of other thing. Okay. So that's the thing. So, but, and I don't have one right now. I'm going to get one. We're going to do a simple one. And then after tomorrow, we're going to do a more complicated one. Okay.